Now, the distribution of F ratios takes a particular form. It's a form that's unlike the T statistic distribution or the Z statistic distribution that was a normal curve. Instead, if the null hypothesis is true in the ANOVA situation, then the value of your F statistic will be around 1. Remember, I demonstrated that before, because you've got no treatment plus error divided by error, so it should be something near 1. Because F ratios are computed from two variances, they're always going to be positive numbers. Remember, variances are variability differences in their squared form, and squared numbers are never negative. So it's one positive number divided by one positive number, so it's always going to be a positive number. It's still, we're comparing values in their squared form. So given these two facts, the F distribution of scores has to look like this. It never goes below 0, and it usually, if the null hypothesis were true, should be centered around 1. Most of the scores, if the null hypothesis were true, just by chance would be about 1. Now, this is a null distribution, so every once in a while, just by bad luck, just by chance, you're going to get F statistics that are much larger than 1. There's no good reason for it. It just might happen because of chance from time to time. But most of the time, you'll find F statistics in this part of the distribution because this is where most of the scores are. And rarely will you get just by chance an F statistic of something much higher than 1. The exact distribution, the exact shape, the exact height of this peak, and the exact number of scores out here in the tail will depend on the number of scores, or in other words, the degrees of freedom. So the table of F values that you should have downloaded and perhaps even printed before you started this module is organized by 2 degrees of freedom. It's labeled in the table as numerator and denominator. I hope that you've printed it so that you can write in on the table between and within, because those are the words we're going to be using, and it's a little confusing to have the table labeled numerator and denominator. So just pencil in, write in, next to the numerator, between, and next to the denominator, within. So we're going to look up the critical F values that we should have gotten in this situation about the cell phone experiment in the table corresponding to the degrees of freedom that we had in our example, which were 2 and 12. So here's an example of what the table looks like. You've got degrees of freedom numerator and degrees of freedom denominator, but remember, we're labeling that between and within. So between, within. In order to find the correct critical F statistic for this example, we use between and within degrees of freedom that we computed before, 2 and 12. We come to our table and we figure out 2 and 12, where they intersect are these two values here. The value in normal face is the value if your critical alpha is 0.05, and the bold face value is the one that you would use if you had an alpha of 0.01. So we could use either 3.88 or 6.93, depending on how stringent of an alpha value we wanted to use. So if the null hypothesis were true, only 5% of all the possible scores from the null distribution would yield an F statistic above 3.88. Right here, marked in your chart right here. And only 1% would yield an F statistic above 6.93. This second value, which is marked right here. So, if the null hypothesis were true, and the treatment really didn't do anything, and all the populations that you drew samples from were really the same, you would expect most of the time to find an F statistic that was around 1. It might be a little higher because of the particular degrees of freedom we have here, but you would expect it to be somewhere in this region. Every once in a while, just because of bad luck, just because of chance, you might find an F value that's much higher than this. But if you find an F value much higher than this, you assume it's not because of chance. Instead, you assume that means there really is a difference between some of your groups. And so we reject the null hypothesis, and we say, even though it's possible that we just got this F value really big by chance, more likely what we think is that the treatments worked, and there is some difference in the populations of these treated values. So let's walk through an example of hypothesis testing. Oh my goodness, we've done all the steps of an ANOVA, so let's put them together to perform a full-blown hypothesis test. In this research study, let's use the question, what method of studying best helps students learn material before taking a test? We'll have 4 conditions here. Some might read the material once, some might read the material twice, some are asked to answer questions that have already been written, and some students are asked to create their own questions and answer those. Here are 4 conditions. Read once, read and reread, answer prepared questions, create and answer questions. I have given you all of these values here for the sake of expediency, but you know how to get these. You know how to compute the total n and the big G and the sum of x squared and the t and the m and the ss. And you may be asked to do that on homework or on a test. So please be prepared. Don't forget what these represent, even though I'm giving them to you here. Step 1. State the hypotheses and select an alpha level. The null hypothesis is that the mean of the first group equals the mean of the second group equals the mean of the third group equals the mean of the fourth group. All the groups are the same because none of the treatments have any difference compared to each other in the situation where the null hypothesis is true. In the alternative hypothesis, we say, in words, at least one of the treatment means is different. In this situation, let's use an alpha of 0.01. For no particular reason, we're just doing that. Step 2, we have to locate the critical region. So in order to do that, we first have to find the degrees of freedom between and the degrees of freedom within, because those are needed in order to look in our table. So the degrees of freedom total in this situation is what? Remember, it's 24 minus 1, 23. And then we split that into 2 parts, the degrees of freedom between and the degrees of freedom within. How do we compute the degrees of freedom between? Remember, it's the number of conditions minus 1. 4 conditions here, minus 1 is 3. The degrees of freedom within, remember this is the number of scores in each condition minus 1. And you add them all up. So you have here 6 scores minus 1 is 5. 6 scores minus 1 is 5. 6 scores minus 1, 6 scores minus 1, 5 and 5 and 5 and 5 is 20. That's the degrees of freedom. But this and this add up to that. Then we look in our table for our critical F. We use degrees of freedom between and degrees of freedom within here on the numerator and denominator. So we use 3 and 20, find the intersection here. And because we chose an alpha of 0.01, we use the bold-faced value, which is 4.94. That's the F value that we need to get an F value of higher than in order to conclude that our ANOVA, that there are differences between these groups. So we draft it out. It looks like this. It peaks around 1. We draw our critical region here at 4.94, and this is the top 1% of scores that we might find if the null hypothesis were true. Just by chance, they might be larger than 4.94, but most of the time, they're not. Most of the time, 99% of the time, they're going to be lower than 4.94. And so if we get one that's higher, it's possible 1% of the time it could just be a random error because of chance. But more likely than not, if we get one that's in this critical region, it's because there's a difference, a real difference between these groups. One of the treatments, at least one of the treatments, worked. Step 3 is to compute the F ratio. So remember, we have an ANOVA summary table down here with SS, DF, and MS. We have to figure out steps 1 through 3, 4, 5, 6, 7, 8, and F. Well, we already figured out the degrees of freedom, remember? Because we had to do that in order to find the critical F value. So let's now figure out the sum of squares. Here are our formulas. The sum of the x squared minus g squared over n, that is 1298 right there. G squared, 168 squared, divided by the big N, 24, equals 122. The second one is the sum of squares within treatments, which in other words is the sum of squares that's inside each treatment. So the sum of squares here, plus this one here, plus this one here, plus this one here, 20, 20, 14, and 8 is 62. And the sum of squares between is this somewhat complicated formula where we have to take the t for each group and square it and put it over the n of that group and then sum all of those up. So we take this t, square it, divided by the n size in this group, which is 6. The t here squared divided by 6, t squared here divided by 6, t squared here divided by 6, and add all of those up. So 30 squared over 6, 36 squared over 6, 48 squared over 6, 54 squared over 6. And then finally we subtract g squared over n. This g is 168 squared over big N, 24, down here. If we carry all of this through, we get 60. So let's take those three values, put them in the table right here, and then finally we need to figure out our mean squares, our variance, our variability here, which is, of course, as you know, SS over DF. So we're figuring out that SS over DF for between and SS over DF within. So 60 over 3 is, as I showed you up here, the formulas. 60 over 3 is 20, and 62 over 20 is 3.1. So we put those in the table there. And the last step, step 9 of the ANOVA test, is to figure out 20 divided by 3.1. MS between over MS within, or variability between over variability within, and that equals 6.45. If you put that here in the table, then you've completed your entire ANOVA test. We have to now, as step 4, figure out what to do with this 6.45. If we look at our original distribution, we marked off the critical region as anything above 4.94. Our obtained value was here, which means we reject the null hypothesis and we say we obtained a value that we would not expect to get by chance if the null hypothesis were true. Therefore, we conclude that there is a significant treatment effect. In other words, there's at least one mean difference between those four groups. But we don't yet know which two means are different. All we know is that across those four conditions of reading once, reading twice, answering pre-written questions and answering questions that you've written yourself, all we know is that there's a difference somewhere. But we still have to figure out where is the difference. In order to do that, we run what are called post hoc tests. Post hoc is Latin for after the fact. So after we've run our ANOVA, then we can run these after the fact tests, these post hoc tests. Remember, the ANOVA compares all the individual mean differences simultaneously in one test. So all the four groups' differences are compared at once, and we have one alpha level, but a significant F ratio indicates that at least one difference in the means is statistically significant, but it doesn't tell us which means differ significantly from each other, and so we run these post hoc tests to tell us which mean differences are significant and which ones are not. But note that you should only perform the post hoc tests if you rejected the null hypothesis. If you didn't, that means there are no differences, and there's no point asking where are the differences if there are no differences. So this test answers the question, where are the differences? Now before I show you how to calculate that, I want to show you why this, or basically how this works and why it's okay. Our post hoc tests actually do the same thing as individual t-tests would do. It compares population 1 versus population 2, population 2 versus population 3, and population 1 versus population 3 in 3 different tests. I told you before that we should never do that because it influences our type 1 error rate. It inflates it a lot. in this situation, the risk of type 1 error accumulates and is called the experiment-wise alpha level. In other words, across your entire experiment running multiple tests, you've got the alpha of 0.05 plus the alpha of 0.05 plus the alpha of 0.05, and you end up with an inflated error rate of 15% of the time. So, increasing the number of hypothesis tests increase the total probability of making a type 1 error, but post hoc tests use special methods to try to control that experiment-wise type 1 error rate and keep it lower than it should be if we had just not made any kind of correction. So it would be about 15% error rate if we didn't make a correction, but the post hoc tests use special methods to correct for that. Tukey's honestly significant difference, abbreviated HSD, Tukey's HSD is one kind of post hoc. There are dozens upon dozens of post hoc tests that you can run that try to correct for that inflated error rate in different ways. But this is a relatively simple one, so we're going to use it. The Tukey's HSD provides for you a single value that determines the minimum difference between treatment means that's necessary in order to claim statistical significance. A difference that's large enough that the probability is less than the alpha experiment-wise. Let me say that in clearer terms. If you compute the HSD, it gives you a number, and you compare your mean difference for first group minus second group, first group minus third group, second group minus third group. You compare each of those differences against this value, whatever this is, and you see if your difference is bigger than this, then it's a real difference, and if it's not, then it's not a real difference. And then we've controlled for the alpha across the whole experiment by computing one value that's a critical value against which we can compare all of our other differences. Now, in order to compute this, the formula here has a Q. This Q is found in another table that I've asked you to download before you start this module, called table B.5. The sample size, N, here, must be the same size in every sample of your experiment for this particular test to work. So if one of your groups had like 20 and another one had 22, then you couldn't use this HSD test. You'd have to use a different type of post hoc. But here, in this example, we have the same size groups for each of the 4 conditions. Remember, each one had 6 people in it, and so we could put this value down here as 6. But before we run that, we have to figure out what is our Q. The value for Q comes from this table B.5, like I mentioned, and in order to find it, you need 2 pieces of information. The first one is K, the number of treatments, and the second one is the degrees of freedom for the error term. You should remember that the degrees of freedom for the error term is DFW. You hopefully have printed this out, and you can write a W up here or within in order to remind yourself that this degrees of freedom for the error term is DFW, degrees of freedom within. We have 4 conditions, 4 numbers of treatments. The first one was read the material once, the second one was read the material twice, the third one was answer questions somebody else prepared for you, and the fourth one was answer questions you wrote yourself. So we find the intersection between the number of treatments and DFW, which we computed as 20. So we follow this down here to DFW 20, 4 conditions, and these are the 2 values that we could possibly use as Q. But in order to decide which one, we have to use either the light face if our alpha is 0.05, or the bold face if our alpha is 0.01. In this situation, if you remember back, we used an alpha of 0.01, so we should use our Q value with the same alpha, and this right here is the Q that we put into that formula. So here is our HSD, Q is 5.02, mean squares within up here is 3.1, the n size of each condition was 6. You plug all those in, follow it through, and it equals 3.61. Now, what do we do with this? This is the standard against which we compare all of the mean differences. So if Tukey's HSD is 3.61, then which of these differences is significant? Group 1 minus group 2 is a mean difference of 5 minus 6, or a difference of 1. I'm not putting the negative values here because it doesn't matter whether we subtract the second minus the first or the first minus the second. I'm taking the absolute value because I just want to know how far apart the two means are, and they're one distance apart, 1 unit apart. The difference between A and C, which is 5 minus 8, that's a difference of 3. The difference between A and D, the first group and the fourth group, or 5 and 9, 5 minus 9, a difference of 4. And you could compare the rest, B minus C, B minus D, C minus D, and in each of those conditions, if you take the mean and compare them across, and you do all those mean comparisons, you need to see which of these mean differences is larger than 3.61. And you should notice that only one of these is larger than 3.61, so that is the only mean difference, 9 compared to 5, that's actually significantly different from each other. All the rest of these are not different from each other. They are technically, literally different, like none of them are exactly the same. 5, 6, 8, and 9, none of them are the same, but statistically, they are not significantly different from each other. We couldn't conclude that group 1 and group 2 are different from each other because they're too close together compared to how far apart you'd expect them to be just by chance. I want you to now remember that when we went through all of our previous t-test modules, that if we found a significant difference, that only meant it's unlikely to have occurred by chance. It didn't tell us whether it's an important or a big difference, and that's what effect sizes are for. In an ANOVA, we don't run the R-squared like we used to with the t-test, but we run something that's almost the same. It's really interpreted the same, and it's computed very similarly. It's called eta. This is a Greek letter eta squared. So the eta squared computes the percentage of variance that's accounted for by the treatment conditions. Remember, that's the same as how we were interpreting R squared before, the percentage of variance that's accounted for by the independent variable, or by the treatments. So this is a lot like R squared, which was the proportion of variance explained by the treatment effect. It's just computed slightly differently. Here we take the SS between divided by the SS total. Remember that SS between includes all the differences, all the variability here that was between the treatments, between meaning because of the treatment effects. So this is the variability that's because of the treatment differences between the one condition and the others. If we take that treatment effect size and we divide it by all the total differences that we see across all the scores in the study, then this number divided by this number tells us that 0.492 is our eta squared. How would we interpret this? Hopefully you would remember that when interpreting an R squared, we would say 49% of the variability in people's test scores after they studied in these different ways can be attributed to the particular way in which they studied. We interpret the eta squared in the same way. So we'd say 49% of the variability in these students' test scores can be attributed to their treatment condition, or can be attributed to the type of study condition that they were placed in. All right, after we finish all of these steps, we have to write it up in the literature. In order to do that, we have to put the means and standard deviations for each of the conditions in a text, table, or graph. In most of the situations in this class, I'm going to expect you to put it in a table like this. And then in addition to that, you'll reference in your write-up that you can find the means and standard deviations in this table or in the graph that you've drawn or whatever. You also include the results of the ANOVA test with the F and degrees of freedom and the p-value, and the eta squared. So here's an example. The means and standard deviations of each condition are presented in Table 1. So you've referenced the table. The analysis of variance indicates that there are significant differences among the 4 study strategies. Then you put a comma. You italicize your F, and you put inside the F the degrees of freedom between and the degrees of freedom within. You then put equals what the F value is, comma, P less than 0.01. Then you list your eta squared, 0.492. And you would say what your post hoc test showed if you ran them, if your ANOVA was significant. Tukey's HSD post hoc analysis revealed that creating and answering questions was better than reading only once, with a P less than 0.01. Before we wrap up this module, there's a couple of reminders I want to give you. These are things we've talked about lots of times throughout the course. But here I want to show you that if you had 2 very similar experiments, but the variability in the treatment types was large in one and small in another, you would draw very different conclusions from your ANOVAs. So here, treatment 1 and treatment 2 are quite, they're the same distance apart, 8 versus 12, as in experiment B, where treatments 1 and 2 are also 8 versus 12. But in the first experiment, you've got scores that are very close to each other in each of the 2 conditions. In experiment B, the scores are much more variable, much further apart. If you graph this visually, you'll see something that we've seen many times before. If you cluster all the scores together, that's these, and all the scores here, that's these, it's quite easy to see between treatments that there's a mean difference between 8 and 12. That 4-point difference becomes very obvious. Your statistic should find that there's a big difference between them as well. But the mean of your white scores and the mean of the teal scores down here is the same distance apart, but when you compare it to the amount of error variability, it's very difficult for your statistic to determine whether this 4-point difference is meaningful or if it's more than you'd expect just by chance. So my question is, would you expect to find a significant F ratio in either one of these experiments? And why? Hopefully you would recognize that this would have a significant F, because this group and this group are obviously different. In fact, if you compute the F, it's 83.96. That's an enormous F, way bigger than 1. In experiment B, you've got an F statistic that's very close to 1, just what you would expect to find just by chance, because these scores are so spread out and overlapping that you can barely tell a difference between the 2 groups. The point here is to help you see that the numerator of the F statistic is the same in both situations, 56 and 56, because that represents the difference between 8 and 12 as the mean difference in these 2 conditions. The denominator measures the variance of scores inside each treatment. So here, there's very little variability inside of this treatment and very little variability inside this treatment. But here you can see there's a lot of variability inside the 2 treatments. The white ones are spread far apart and the teal ones are spread far apart. And so you find a lot more variability just by chance, the error variability. So it's bad to have a lot of noise within your conditions, because when you pit against each other the treatment difference and the random error differences, you will see that you'll get a very large score if the differences are far apart, and a very small score if the differences are not that far apart. There's another principle here I just want to drive home, and that is that if you only have 2 conditions in your factor, in your independent variable, you can run either a t-test or an f-test. And in fact, you'll always get the same decision if you use the same alpha, because f will always be equal to t squared. if you look in this example, we might use a two-tailed t that results in critical values of plus or minus 2.101. If you square that value, 2.101 squared is equal to the critical F statistic of 4.41, and that will be in this one tail because an F value always has only one tail. There is no such thing as a negative F value. So for any value of alpha, the T critical squared is also going to be equal to the F critical. So whatever your computed statistic is and whatever your critical statistic is, they're always going to be closely related to each other in that the T squared is equal to the F. And the reason for this is because this is an analysis of variance, the standard deviation still in its squared form. The t-test is comparing the difference between two means in terms of standard deviations, which are no longer in the squared form. So the reason why this is squared compared to this is because here we're looking at differences in terms of standard deviations, and here we're looking at differences in terms of variance. This allows us to compute more than two mean differences. This doesn't. But if you have only two mean differences to compare, you can run either a t-test or an f-test, and it will get you the same answer. It will not be the same value. The f and the t won't be the same value, but the conclusion to reject the null hypothesis or to fail to reject the null hypothesis will be the same regardless of which type of test you use. There are some assumptions associated with the independent measures ANOVA. Those include the observations within each sample have to be independent. The number of scores in each condition should be equal, but they don't have to be. The population from which the samples are selected must be normal, but we sometimes violate this assumption if the sample sizes are large, like greater than 30. It's usually okay. The populations from which the samples are selected must have equal variances. That's an assumption called homogeneity of variance. Remember, in our independent measures t-test, we had to compute this using our Fmax. If you violate the assumption of homogeneity of variance, then it risks invalidating your test results. So you can't trust your test if you violated the homogeneity of variance assumption and the variance of your groups is too big, are too different from each other. Now, before we end our module here, I want you to work through one more practice exercise. In this situation, researchers want to compare happiness levels for those who are the richest third of Americans, the middle third, and the poorest third. Are there any significant differences between the classes? And where are they? Here are your data. The richest, the middle, and the poorest. These are happiness scores. I want you to perform the 4 steps of your hypothesis test using an alpha of 0.05. I recommend that as you do that, you put your results in an ANOVA table like this, with all 9 of these steps articulated. If your ANOVA is significant, then you should calculate a post hoc test as well, and calculate a measure of effect size, and then write it up as if for publication. Please pause your video, work through this example, and then when you're ready, move on to see the answers. Here are the answers to the ANOVA. You've got, in order to figure this out, you have to compute the mean of each condition, the sum of squares of each condition, the t of each condition, and also the n size of each condition, the number of conditions, the total n of your whole group, which I didn't write here, the g, the sum of x squared, and follow all 9 of those formulas in order to fill in your ANOVA summary table like this with your obtained F as 20.94. You should have found a critical F of 3.88. Your obtained F is much larger than your critical F, so you reject the null hypothesis and run some follow-up tests. Your post hoc tests use this Q. You put in these values. You get a HSD of 1.19, and you have to compare the means of the richest to the middle, the richest to the poorest, and the middle to the poorest. Those are your three differences, and you have to see which ones of these are larger than here. This and this are significant because they are larger than this critical value. This one is not larger than this critical value, so the groups here versus here and here versus here are significant. In other words, if you have a certain amount of money above being very poor, it doesn't matter if you are in the middle or the richest class of people, you are just as happy as each other. But if you're in the poorest class, you are less happy than the other classes. You would also compute your eta squared. You take the between sum of squares and the total sum of squares, and you pit them against each other, 4.77. You might interpret this as practice by saying 77% of the variability in happiness scores is accounted for by which class you're in. And then finally, you would write up a sentence, as is for publication. It might say something like, the means and standard deviations are listed in Table 1, and you'd put Table 1, and you'd list the means and standard deviations, and then you'd say, an ANOVA test indicated that there was at least one mean difference between the classes of people, comma, F, degrees of freedom, then your p-value less than 0.05, and then your eta squared, 0.77, and then you'd put a period and you'd say post hoc tests, you'd probably specify the type. Tukey's HSD post hoc tests indicated that the richest Americans were happier than the poorest, and the middle Americans were happier than the poorest. But the richest and the middle were not different from each other. And that's how you do it.